So in this video, we're going to solve a force of gravity problem in two dimensions. Here we have three masses, mass A, B, and C, and they all have the same mass. So we'll write that here. So the mass of each is 1 times 10 to the 20 kilograms. So the force of gravity is quite a weak force. So therefore, in order to get an answer that approaches any kind of significant value, we use a large mass. Separating the masses, so between A and B, we have 1 times 10 to the 9 meters. So again, these are celestial kind of distances. This is something that could be in space. And over here, we have 2 times 10 to the 9. So the first thing I'm going to do is we need to know how far apart A and B and C are, because we know already the distances between the other two objects. So we know the distance between B and C and A and B. So we need to complete the problem first by finding this distance. So I'll call this x for now. So we're going to look for x using the Pythagorean theorem. So x is equal to the square root of 1 times 10 to the 9 squared plus 2 times 10 to the 9 squared. And when you work that out, it becomes 2.2 times 10 to the 9 squared. 2.2 times 10 to the 9 meters. Now, what else will be useful is this angle here. So what I'm referring to is there's an angle right there, and we're going to look for that by using the tan ratio. And the reason why I use the tan ratio is because we have been given these sides. We can use any of the three trig ratios, so sine and cos are still okay. But I like the tan ratio because these numbers are given to us, whereas the x value is something that we found and rounded. And so that means that the accuracy of the angle measurement is not going to be it's not going to be there. So the angle is the inverse tan of the ratio of the opposite side over the adjacent side. Well, this side is 2 times bigger than this side, so that'll be 2. And this works out to be 63.4 degrees. So let's just put these into our givens now so that we have room to solve the problem. So I'm just going to erase some of this. So erase that and that. Actually, I'll erase all of it. And then I'll rewrite that here. So theta is equal to 63.4. And x is equal to 2.2 times 10 to the 9 meters. Okay, so the first thing we do whenever we see a problem in two dimensions like this is that we break it up into its x and y components. So the first thing I'm going to do is look at the x-axis. And there are only two masses. There is, and not only do we look at only what's happening in the x-axis, and so don't get confused by this variable. It's not this axis here, but it's the horizontal axis. So maybe we'll label that to be horizontal axis instead. So this is the horizontal. So in the horizontal, we have to treat each pair of objects separately. So the question is, what is happening to object A? So I want to first figure out what is the force of gravity between A and B, and then add it to what is happening to the force of gravity between A and C in the horizontal direction only. So the force of gravity, and I won't put a subscript G because the only force acting on these objects in this question is gravity. So the force of gravity on A is equal to the force of gravity due to A and B plus the force of gravity due to A and C. And this is all in the x direction, or the horizontal. So Fax is equal to, well, between A and B, we can use Newton's universal gravitation formula. And then we'll add it to Newton's universal gravitational formula for the masses A and C. Now, what's interesting here is that we need to have solved x in order to do this problem because A and C are x distance apart. So that's in this part right here. Also, we're only looking at the x direction, so we need to take the component of this in the x direction, or the horizontal direction. So I should actually rewrite that so I can put that in there. So let's rewrite that. So we have G MA MC over x squared. And then the component of this is cos theta. Now let's look at our signs here. Gravity is a pulling force, so the force of gravity on A due to B will be to the right because B will pull on A to the right. The component of gravity in the horizontal due to C is also pulling to the right. So both of these, if we assume the right is positive, which I often do, both of these will be positive, which they are in this case. So G and MA, let's factor that out, and we'll also put it in here. So this is G, and MA is given, it's 1 times 10 to the 20. In fact, MA and MB and MC are all the same, so why don't we just factor all that out? And so what we're left with, so this is G, MA, MB. So we've taken that out, and what we're left with is 1 over RAB squared plus, now GMA MC is also this, so what we're left with is cos theta over x squared. And remember that RAB is equal to 1 times 10 to the 9. X is equal to 2.2 times 10 to the 9. And theta is equal to 63.4. And when you calculate that, you get 7.3 times 10 to the 11 newtons to the right, because we said that the pulling force was happening to the right in a positive direction, and this answer is positive, so therefore it must be to the right. Okay, so let's look at what's happening in the vertical direction. In the vertical direction, we only have this interaction because B cannot pull on A up or down. It's only C which is pulling on A up. So we're going to have a similar statement here without the first term. We're just going to have FAC subscript Y because that is going to be C's contribution. So let's write that here in the vertical direction. We have FA subscript Y is equal to FAC Y. And this is equal to G MA MC over x squared Now, before it was cos theta, this time it's going to be sine theta because we want that vertical part of the triangle. So again, these variables were the same as before. In fact, this whole thing was the same as before, except the only difference is this. And if you multiply it by this new value, you get 1.23 times 10 to the 11. Now, what's the direction? Well, normally positive is up, and we've assigned that to be up. Just by looking at the drawing, we see that gravity, again, can only pull on A, and because C is above it, it's going to pull A up. So this answer is going to be up. So now we'll put them together. So what is the net force due to gravity on A? Well, it's the Pythagorean sum of FAX squared plus FAY squared. And that works out to be 7.4 times 10 to the 11 newtons. Because it's a vector, we need an angle. So we'll call this alpha. So what we have here is we have a C and B are both pulling on A to the right. So that vector is going to be pretty long. So that I'm anticipating my overall vector situation to look kind of like this. We've got a really long pull vector and not so long pull vector vertically. So we have a long pull vector horizontally and a not so long pull vector vertically. So this is our FA net, and so this will be alpha. So this is not the triangle that we had before. This is made up of the force of gravity rather than the distances. So what is our angle here? Well, again, I'm going to use the inverse tan. So I'm going to take the magnitude of the vertical component over the magnitude of the horizontal, and that gives me 9.6. So it is a small angle because this is smaller than this side here. So our overall statement, so therefore, the force of gravity on mass A is 7.4 times 10 to the 11 newtons forward, 9.6 degrees up. Now you can do this exact same problem solving technique, finding the force of gravity on B. And in fact, it would be easier for B because on the horizontal side, there would just be this interaction. The vertical side would just be this interaction, and then you would use Pythagorean theorem to solve it again. And then you could do the same thing for C, but you've already done most of the work because what's happening to C is pretty much the opposite of what's happening to A. So where A is being pulled up in this direction, C will be pulled down in this direction. So there's some symmetry here. Thank you for watching.